Back in Unit 1, you were introduced to how the programming process works, and then in Unit 2, you learned some actual programming. Now that you understand a little bit more about both of these things, let's take a step back. In Unit 1, you learned that a program is written in a high-level programming language with lots of abstractions like words and symbols that give meaning for humans, but ultimately for the computer to understand the program, it's got to be crunched down into the lowest level possible, which is binary. We didn't really make too big of a deal about it at the time, but now we really need to take a much closer look at what binary is and how it works. We've already talked about binary several times in this course, and by now you probably have the idea that binary is a pretty big deal when it comes to computers and to computer science. We've talked about how it is, and I'll use the term dichotomous. Binary is all about a dichotomous relationship, meaning there are only two possible states. There's a 0 or a 1. There's an on or an off. There's a true or a false. When we talk about Scratch, and we use those Boolean, those hexagon-shaped blocks, we know that those, regardless of how complex or how many of them are nested together, are going to yield one value, and it's either going to be true or false. And that's kind of similar to a traditional light switch. Not talking about a dimmer switch or anything fancy, but a light switch that can be either up to on or down to off. We've already talked about those types of things, so let's carry that relationship out to some other relationships. You are going to, if you haven't already, play a game called 20 Questions. And if you haven't played this, sometimes this game is actually called Yes or No, because the questions that you ask must be answered by either yes or no. And there can be no other answer. And you have 20 guesses to figure out what the other person is thinking of, or the computer is thinking of. And so you will definitely get a chance, if you haven't ever played this, you'll get a chance to do that later on in this lesson. The other examples would be directions, left and right, your hands. Usually you are either predominantly right-handed or predominantly left-handed. Yes, there are some people who are ambidextrous and who are equally good with both, but typically we have one strong side. So binary code is essentially the on and off condition of billions and billions of teeny tiny little switches in the circuitry of a processor, and we represent those with ones and zeros. And so you can see an example of what that looks like here on the screen. Unlike something like, say, the alphabet, where we have characters, we're not talking about capital and lowercase, but just the characters that we have at our disposal, we can combine the letters A, B, C, D, E, F, G, all the way on to Z to create our words. And so we have like 26 different characters that we can combine. Well, binary, we only have 2 different characters. By, the prefix meaning 2, we only have ones and zeros to represent what we are trying to show. Just in case you don't remember, just a little refresher, that each of these zeros and ones is referred to as a bit. All right, so 1, 2, 3, 4, 5. Right here we have 5 bits. And if you don't remember where the term bits comes from, it's kind of a contraction almost between the word binary and then digit. So the B from binary, the it from digit, forms the word bit. And that's what we use to describe individual ones and zeros. So why do we talk about bits? The purpose of bits is to represent something digitally. All right, usually if you think about the difference between a digital clock and a clock with hands, a digital clock has all of these little segments. Having all of the segments on will yield the number 8. We'll show you the number 8. But then if you erase, say, the side ones, you would end up with something like this, and you would end up with a 3, right? So all those little segments are there. It's just a question of which one is turned on and which ones are turned off. So that's how we represent something digitally. All right, so we've already talked about bits and where that word comes from. It kind of got made up or coined to go along with computers, but you're probably more familiar with the word bytes because we actually talk about groups of bits more often than we really refer to the individual bits themselves. You might have a 1 gigabyte flash drive. You might have a file. For example, when you submit your video to the College Board, your maximum size is 30 megabytes. So really, we talk about bytes more often than we talk about bits. And bytes are typically 8 bits. Okay, and when we talk a little bit more about bits and bytes, it'll make a little bit more sense. But with binary code, we've been talking about how it's only ones and zeros. And so you might be thinking that, well, because it's only ones and zeros, there must be only a limited number of values that we could represent with those. And for the rest of this lesson, we're going to talk about how we can use binary code to represent really any number that we want. All right, so our number system is base 10. All right, that's how, if you know that we refer to the word decimal, right? Deci. Surely you recognize that from like when you've studied the metric system or something like that, that deci, the prefix, is going to mean tenth. All right, so decimal means that we are in base 10. All right, and in base 10, we have 10 digits that we can work with. So, and you might think, well, 10, no, we only go up to 9. But don't forget that 0 counts. As a matter of fact, 0 counts a lot because our number system would not work without the 0 as a placeholder. So 0 does count. So counting 0, there are the digits 0 through 9. So there are 10 possible digits that we have. That's how we are able to create not just 0, 1, 10, and 100, but 9 and 99 and 8 and 7 and 72 and all of those different numbers that come in between. We are able to combine 10 different digits, an infinite number of combinations, to create numbers. So that's different from the binary system. We already talked about how we only have zeros and ones, and so we can only use zeros and ones to represent numbers. Binary code uses an 8-bit system, meaning there are going to be 8 bits grouped together to form a byte. You can almost think of a byte as a word, kind of how we group letters together to make a word, and certain letters and certain combinations make up all the words that we know. So words in computer talk have 8 characters, 8 bits. All right, so what we do is, and you have a really excellent video to watch on this, and I'll actually jump to show you actually how this works on an Excel spreadsheet. But for right now, suffice it to say that every place in our base 10 number system is based on 10 raised to some power. All right, in the ones place, it's 10 raised to the 0 power. In the second place, and this for us, this is the tens place, it's 10 raised to the first power. In the third place, for us, this is 10 raised to the second power, or the hundreds place. 10 squared is 100. Okay, spoiler alert. Next one is actually 10 to the third, or the thousands place. If you weren't sure what I meant by that, by 10 to the 0 power, anything to the 0 power is 1. So that's how it works in base 10. So for binary, what we've got here is 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the, guess it, yes, the third power, 2 to the fourth, and all the way out to 2 to the 7th power. All right, 2 to the 7th power is 128. So that's how the binary system works. It's exactly the same as ours, except the base here is 2 instead of 10. All right? So it's really not that much different. The only difference is the base. And that's why it's base 2 and not base 10. All right, let's try and look at an example. The number 41. All right, so 41, just to break it down over here, is, and this is a base 10 number, by the way, they will always specify on the test, they will tell you this is a decimal number, or this is a hexadecimal number, or this is a binary number. They will always tell you what base the number is. So this one, I'm going to tell you, since it doesn't say on the slide, this is a base 10 number, which means that this 1 represents how many groups of 10 to the 0 power, and this 4 represents how many groups of 10 to the first power. All right, so 1 group of 1, 4 groups of 10, added together gives us a value of 41. That's how we come up with this, okay? So as a reminder, this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the 6. As you might have guessed, I really don't have to go out this far, but I'm just going to mark them all just so you know. So 2 to the 7th is 128. All right, so these are our place values for base 2. So the question is, how do we take these numbers and group them up to make a total of 41? All right, so we have to ask ourselves, how many groups of 128 can I make with 41? Okay, well, the answer clearly is 0. How many groups of 64 can I make with the number 41? The answer is absolutely 0. Okay, not evenly anyways. All right, how many groups of 32 can I take out of 41? Aha, I can actually take one away. All right, so what happens is I will end up with 1 in the 32's place. All right, and so I have eliminated 32, which means that I've got 9 left. Okay, 41 minus 32 gives me 9. So I've still got to show 9. I'm only showing 32 right now. So how many groups of 9 can I make from 16? None. How many groups of 9 can I make from 8? 1, right? Okay, so now I've gone from 9, I've taken out a group of 8, and I'm left with 1. So all I have to do is fill these in with zeros right here and put this switch on. All right, so this is how 001010001 is how I would represent the number 41, the decimal number 41, using binary. Pretty cool, right? All right, a little bit of a simpler example. How would I show the number 1? Well, as you can probably guess, moving from the left to the right, how many groups of 128 can I take out of 1? None. How many groups of 64 can I take out? None. How many groups of 32? None. How many groups of 16? None. 8? None. 4? None. 2? None. But how many groups of 1 can I take out of 1? 1. Look at that. And the question is, in binary, would I write something like 000000001? No. Okay, I could write just the number 1. I don't need to show those leading zeros, just like in base 10. I don't need to show leading zeros because they don't affect the value of the number. So if you see something like this on the test, and they give you the number 1, you better double check to make sure, is that a decimal number? Is that a binary number? Is that a hexadecimal number? Don't worry if you don't know hexadecimal. We're going to get to that later. You can't tell unless you are told, okay, what base that number has. So in this case, this is a decimal number 1, and the equivalent to it in the binary system is 1. So the biggest number that we can represent with an 8-bit number is 255. And you might recognize that number. 255 is actually a pretty significant number. If you have ever worked with colors, say in an application like Photoshop or something like that, you'll know that colors are mixed using a scale of 255. 255 for red, that would be the maximum amount of red, green, and blue. And so that's pretty significant. And the reason for that is that if I add all of these numbers up, right? If I add all of these numbers, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, I will get the number 255. Okay? And that actually means that I can represent 256 total values. How is that? I thought the biggest number was 255. Yes, it is, but don't forget I can also represent the value 0. That counts. 0 counts, especially in binary. All right, so I can represent 256 total values. However, in the grand scheme of things, when we are talking about huge amounts of circuits and the need to represent far bigger numbers than 255, that's where we get to this point where maybe we're moving beyond 8-bit numbers. Maybe we're looking more at 16-bit numbers or 64-bit numbers. We skipped 32, but that's absolutely an option. You can see over here, so let's say it's a 16-bit number. Well, here's the number of values, like we have 255 up to here that we can represent, But look at how much this is increasing. This is 2 to the 8th power, 2 to the 9th, 2 to the 10th, 2 to the 11th, 12th, 13, 14, 2 to the 15th power, right? So we have hugely, hugely increased the numbers that we can represent, okay, with just a 16-bit number. And that's half of what we can represent with, actually, that's not the correct math, with 32 bits or with 64 bits. With all of these systems, our decimal number system, the 8-bit system, and all the other number systems that we could use for binary, we see something called state space, or the space of potential possibilities. All right, and so in the 8-bit system, we saw that we had up to 255 or 256 distinct possibilities. In our decimal number system, the possibilities increase as the number of place values increases, right? So if we've got 3 place values, the ones, the tens, the 100s place, we can represent 999 different numbers, because the largest digit that could fill these would be a 9, right? It'd be 9 in the hundreds place, 9 in the tens place, and 9 in the ones place. All right, so 999 would be the biggest. And of course, if we were to add in the thousands place over here, we could even add in more. So now we can show 9,999 different values, right? So that's the state space that we have for 3 digits and for 4 digits. A little bit later on in this lesson, you'll watch this really neat video. I'm pretty sure they had this one on Sesame Street too, I'm going to tell you, where this guy makes noodles and he folds them by hand. Like, he's an artisan. The reason that that is shown, the reason why that has any bearing on this lesson at all, because really, noodles, the state space refers to the potential number of noodles that he could make every time he folds the existing noodles in half, okay? And that's a pretty cool relationship. So how does state space grow? We talk about this relationship between the growth that number systems have when we increase place values. This is an exponential type of growth, all right? Where if you've got 1 digit, you can encode 10 different numbers. This is the base 10 system, by the way. 2 digits, you can encode 100 different numbers. 3 digits, you can encode 1,000 different numbers. And so hopefully you see the pattern there. You can see the growth. We've grown from here to here by 10. We've grown from here to here by another 10 or 100. All right, so hopefully you see the pattern. The state space multiplies by 10 every time we add a digit. Well, state space in the binary system is very similar. We still have this exponential growth, right? Because we're raising the exponent every time. And we can see that we have 1 right here, 2 right here, 4 by here. If we increase to 4 bits, we're at 8. 5 bits, we're at 16. All right, and so that's growing by a power of 2 every time, or by an exponent, by 1 in the exponent. So the pattern is the same. The base of each exponential term is the base of that number system, right? So the base of the growth, as we increased state space, and we said it was increasing exponentially by increasing powers of 10. So 10 to the first, 10 to the second, 10 to the third, right? So that base right here is 10. Over here, it's the exact same thing. As we increase state space, we increase the number of values we can represent exponentially as we add place values. And the base for that growth is 2 instead of 10. All right, so you can see what we're looking at here. And I'll show you this in a different way in a little bit. But if you remember back, I'm going to go ahead and say you probably started learning this in 3rd and 4th grade, when your teacher would give you a number like 347. And your teacher would say, I need you to write this number in expanded form. Remember this? I hope so. So you would have to do something like, okay, well, I have to break this number down. I have to know that the 7 is in the ones place. And so that means that is 7. I have to know that the 4 is in the tens place. That means 40. So that means that this number shows 40 plus 7. Then I've got a 3 in the 100s place, so I know that that makes 300. So I know that I have to add 300. So this number in expanded form is 300 plus 40 plus 7, right? And that's what you see right here, okay? And it's just that the expanded form relies on knowing your powers of 2 rather than your powers of 10. Okay, so maybe you're not as familiar with your powers of 2 as you are with your powers of 10, but good news. You don't have to worry about the digits 2 through 9. All you've got is 0 and 1. So that kind of makes up for it. The formula that you see in your lesson is also shown here. And it may look pretty complex. You may not have learned this type of notation or this type of math yet, and that's really not a big deal. I can almost guarantee you that you're not going to see this formula on the exam. But just to give you a little bit of information about it, this right here is the Greek letter sigma. And the Greek letter sigma, whenever you see that in math, it is going to mean summation, actually. Okay, but summation, the first 3 letters are sum. And of course, we know that sum means addition. Okay, we're adding some things up. This number up here, I, represents place value. And it represents whatever the exponent is on the base. All right, so in binary, we said that our first digit was represented by 2 to the 0 power. I is 0. In decimal, we said the first place was represented by 10 to the 0 power. I is 0. We said the second place is represented by 2 to the 1. Now I is 1. Second place is represented by 10 to the first. Now I is 1. Well, guess what? I'm showing I is 2. Now I is 3, okay? And so on and so forth. That is all that means. So as I increases by 1 and the base, you have to know what the base is. You have to know, are you in base 2 or are you in base 10? But basically, every time you add a place value, you are going to add up all the place values that you have to get the value of the number. Okay, so again, like the number that we did, what did I do? 347, something like that. Basically, that means the sum of whatever is in the zeros place, whatever's in the ones place, whatever's in the two place. Let's say our number is 534, right? So it's the sum of whatever's in the 10 to the 0 place, plus whatever's in the 10 to the ones place, plus whatever's in the 10s to the 2s place. Again, I really don't think this formula is going to be on the test for you, but it just means that the way we determine the value of any number in any number system means that we sum up, we add up all of the place values based on whatever the exponent is in that place value as it increases by 1. All right, so the last thing that we need to do is take a look at the same concept that we're talking about, the same base 2 or base 10 type of system, and figure out how this works with decimals. So consider this example right here. You can see that there are 32 characters, either ones or zeros, strung together here. So this is a 32-bit representation of a number. All right, so here we have 10 digits. Technically, you might be tempted to say, well, these numbers are the same. But clearly, you've been doing this whole decimal thing a long time now, I'd venture to guess. And you know clearly that these are two extremely different numbers, very, very different numbers. We might want to assume that when we represent a number in binary, that we might have some place for the decimal. Like somewhere in this range of 32 bits, one of these bits somewhere in here might represent, depending on where that decimal would be, maybe this one might represent the decimal, or maybe this one might represent the decimal. It would seem intuitive, right, that would be the case. However, it's not. Sorry, it just can't be that simple. If it were, this would be what we call fixed point representation, because we would put the decimal point in the same place every single time. And we would have to shift. Let's say this is the one right here. This one represents the decimal point. Okay, and every number that we represent is going to have to fit within this scheme. So we can have this many over here can be before the decimal, and this many over here can be after the decimal. Well, that really limits our ability to show numbers. What if I need a bigger number over here? What if I need more precision over here, like more digits after the decimal? Okay, so I really can't use a fixed point method of representing numbers because it really, really limits the ability to show numbers. And of course, we know that kind of the point of computers is to deal with really large numbers for us. And so that way wouldn't be really effective. So what's done instead is we use what's called a floating point representation. When you declare a variable and you declare an integer, like int or something like that, it is assumed by the computer that you are going to use a floating point number. Okay, so what that means, why is the decimal point floating? Well, it floats because we don't want to limit our number by saying exactly where it has to be. We want the ability to represent all kinds of numbers, really, 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 really small numbers, all the way up to extremely large numbers. And we want to be able to do it with 32 bits. All right, so to explain this, let me go in here very quickly and just refresh your memory on a little something. You love how this trip down memory lane for math. A little something called scientific notation. You may remember this. We might have done something like this. Let's say 3.2 times 10 to the negative 6th. Okay, do you remember doing that? And you knew that what that meant is that you took the number 3.2, and we're going to assume that because it's times 10 to the negative 6, that I'm actually taking this decimal point 4, 5, 6. But I'm hoping you remember what that means. And likewise, if it would have been not a negative 6, but a positive 6, then my decimal point would have moved in the other direction, 6 places. All right, so that's what scientific notation did. Well, they applied the same concept to numbers in the binary system. Okay, so to represent these floating point numbers, here's what they do. There is one specified bit that tells whether this exponent, remember the 6, it was either a positive or a negative 6, this number right here specifies whether it's positive or negative. Okay, this number right here tells what is that exponent. Okay, 10 to the what, or 2 to the what, right? So 10 to the what? This could be a really, really big or a really small number depending on whether it's positive or negative. All right, and then these digits right here represent whatever the number it is that's being multiplied by this 10 to the whatever over here. Okay, and again, look at how big that can be. So this can represent a really small number up to a really, really large number. Okay, now there are little teeny tiny problems with this because you can't represent every single number. All right, so if you remember the word heuristic that we talked about, you could almost say that floating point representation is a heuristic to show the most possible numbers with the greatest range, even though it doesn't technically work for every single number. But anyways, for the exam, I would recommend that you understand why floating point representation is used and what it accomplishes for us and maybe what its limitations are. You don't have to, for example, I don't believe you need to know these vocabulary words right here, although it wouldn't be a bad idea to know them.
Crazy. Stop ripping it. Oh wow. Watch, do it again. It's so weird that it's so straight. It's magic.